Your heating bill is a subscription you never agreed to sign. And the worst part? The technology to eliminate it, or at least gut it, has been sitting in recycling bins, backyards, and forgotten homesteader manuals for over a half-century. Today, I'm going to show you a system built from aluminum cans, a sheet of polycarbonate, and a wooden box that can heat a room in winter using nothing but sunlight. No gas, no electricity, no monthly invoice from anyone. This is the solar pop can heater, and by the time this video is over, you're going to wonder why every south-facing wall in the country doesn't already have one bolted to it. Let's start with the thing you're paying for right now. Natural gas, electric baseboard heat, a forced air furnace that roars to life at 3 in the morning and pushes your meter spinning. The average American household spends between $800 and $1,500 every single winter on space heating alone. That number climbs every year, and the system delivering that heat, the ducts, the burners, the smart thermostats, the service contracts, is a black box. You can't fix it. You can't build it. You can barely understand it. You just pay for it. It breaks, you call a technician. Rates go up, you absorb it. Supply chain hiccups, price spikes, polar vortex, every one of those is a bill that lands in your mailbox. You are a consumer in a system that was designed to keep you consuming. But there is actually a way out. It doesn't require a rooftop solar array. It doesn't require a $30,000 heat pump. It requires cans, aluminum cans, and a Saturday. To understand where this technology came from, we have to go back to the 1970s, specifically to the American energy crisis of 1973, when the OPEC oil embargo sent fuel prices through the roof overnight. Suddenly, ordinary people, farmers, homesteaders, tinkerers, were desperately searching for ways to heat their homes without depending on a supply chain that had just proven it could be switched off by a foreign cartel. In communities across New England, the Midwest, and rural Canada, builders and experimenters started working with what they had. Aluminum was cheap, abundant, and already being thrown away by the millions of units every single day. Someone, and the credit gets passed around, but the community of off-grid homesteaders in places like Vermont and Manitoba were central to it, realized that a column of aluminum cans, painted matte black, placed inside a glazed box and mounted on a south-facing wall, could move a shocking amount of heated air into a room with zero fuel cost and zero moving parts. By the late 1970s, plans were circulating in Organic Gardening magazine, in Mother Earth News, in hand-stapled homesteader newsletters passed between neighbors. This technology was documented, tested, and celebrated long before the first programmable thermostat was ever conceived. Then, cheap oil came back, and with it, the tinkerers went quiet. Here is the physics, and I want you to really understand this, because once you do, you will never look at a black surface in the sun the same way again. Think of sunlight as a delivery truck. It shows up at your wall every clear day, loaded with energy, and it will drop that energy off whether you're ready for it or not. The question is, do you have a system to capture it, or does it just bounce off your siding and disappear? A matte black surface is one of the most efficient solar absorbers that exists. It reflects almost nothing. It drinks in radiant energy and converts it to heat. Now, take a column of black aluminum cans, stacked end to end, bottom drilled out so that air can flow straight through, and seal it inside a glazed box. The glazing lets shortwave solar radiation in, but traps the long-wave infrared heat that the black cans radiate back. This is the greenhouse effect, operating at the scale of a window box, entirely on purpose. Here is the mechanism that makes it actually work as a heater, not just a warm box. Convection. Cold air is denser than warm air. When you cut a low vent at the bottom of the collector box and a high vent at the top, both passing through your wall into the room, you create a loop. Cold room air falls, gets pulled in through the bottom vent, travels up through the heated can columns, gets superheated by the black aluminum, and exits through the top vent into the room. No fan, no pump, no electricity. The temperature difference does all the work. This is called a thermosiphon. It is one of the most elegant and ancient principles in thermal engineering. The building itself becomes the engine, the sun is the fuel, and aluminum cans are the heat exchanger. The performance depends on three variables: the surface area of your collector, the temperature delta between the interior of the box and the room, and the glazing's ability to trap that heat. On a clear winter day with good sun angle, the air exiting the top vent of a well-built collector can reach temperatures between 120 and 160 degrees Fahrenheit, consistently, passively, every single day the sun shines. Let's talk real numbers, because the skeptics always show up in the comments, and they deserve an answer. A well-constructed pop can collector covering roughly 20 square feet of south-facing wall has been documented by hobbyist builders to deliver between 1,000 and 3,000 BTUs of useful heat output under good sun conditions. That is meaningful room-scale heating. Community build projects tracked by groups like the Solar Schoolhouse and documented on open builder forums have reported wall-mounted collectors consistently bringing small rooms from 55 degrees Fahrenheit to 68 degrees Fahrenheit on sunny winter days without any supplemental heat source. Compare that to what you are currently paying. A single propane wall heater running for 6 hours to keep a workshop at livable temperature will burn through roughly $3 to $5 of fuel per day in average U.S. conditions. Over a 4-month heating season, that is $360 to $600 for one room. The pop can collector costs $0 to run. The sun does not send invoices. The efficiency conversation is also worth having directly. Photovoltaic solar panels, the ones that cost $15,000 to $20,000 to install on your roof, convert roughly 15 to 22% of the sunlight that hits them into electricity. A solar thermal collector, like this one, converts solar radiation into usable heat at efficiencies that builders consistently measure above 60%, and in optimal configurations, higher. You are not fighting the physics of the photovoltaic effect, you are just using black metal to get hot. The math is stark. Thermal solar is dramatically more efficient at delivering heat than photovoltaic is at delivering the electricity you'd use to run a heater. And the material cost? Aluminum cans are free if you collect them, or nearly free if you buy them in bulk at scrap prices. A sheet of polycarbonate twin-wall glazing, the same stuff used in greenhouse roofs, runs $30 to $60 for a panel sized for a serious collector. Lumber for the frame, $40 to $80 depending on your local prices. Total out-of-pocket, under $150 for a system that will operate for decades with zero maintenance and zero fuel cost. The difference is not marginal improvement, it is a fundamentally different relationship with heat. So here is the question you are asking right now. The physics are not complicated. The materials are cheaper than a car payment. The history goes back half a century. Builders all over the world have documented this working. So why is this not on every house? Why is this not in every hardware store? Why is this not in the building code as a standard requirement? That is exactly the right question. The answer has layers, and none of them are flattering. The first layer is economic. There is no industry that profits from you building a pop can heater. The aluminum cans are already made. The lumber comes from a local yard. The polycarbonate sheet is a one-time purchase with no service contract. Once it is on your wall, no utility company meters it, no technician inspects it, no manufacturer sells you replacement parts. The system exists entirely outside the revenue stream of the energy economy. And that, quietly, is why it never got a marketing budget. It never got an industry association. It never got a lobbying group writing its name into the energy efficiency tax credit forms. The second layer is building codes. This is where it gets more frustrating. In many jurisdictions, adding a wall-mounted solar collector to your home technically requires a permit. The permit requires a licensed contractor in some cases. The contractor has to work from approved plans. Approved plans require engineering stamps. Suddenly, a $150 project is gated behind a process that costs more than a gas furnace installation. And the inspectors have zero training on passive solar thermal because the industry that trains inspectors is the same industry that sells furnaces. Post-war America made a decisive choice: cheap oil, mass-manufactured housing, centralized utility infrastructure. That choice was not made because passive solar failed. It was made because passive solar could not be turned into a subscription. You cannot meter the sun. You cannot create a recurring billing relationship from a box of painted cans. So the investment went elsewhere, the expertise atrophied, and 2 generations of builders grew up never learning that this was even possible. Here is the crystalline truth underneath it all. No industry profits when you build one of these yourself. That is not an accident. That is the filter. Technologies that empower individuals to permanently exit the consumption loop do not receive R&D funding, do not receive code pathways, and do not receive prime-time advertising. The ones that do, heat pumps, smart thermostats, solar leasing programs, all have one thing in common. They keep you a customer. We traded 60% thermal efficiency for 20% photovoltaic efficiency, in part because the latter required billion-dollar manufacturing infrastructure, installation labor, and financing products. The former required a drill, some cans, and an afternoon. Here is exactly how you build one. I want you to be able to start this weekend. You need a rectangular wooden frame. Think of it like building a shallow cabinet. A collector that is 4 feet wide and 6 feet tall gives you roughly 24 square feet of collection area, which is a solid starting size for a single-room supplement. Use 2x6 lumber for the frame to give yourself depth for the can columns and insulation. Line the back and sides with rigid foam insulation, 1.5-inch polyiso or XPS, then cover the insulated back panel with a thin sheet of black painted plywood or sheet metal. This is your absorber backing. The cans, you need roughly 200 to 240 standard 12-ounce aluminum cans for a collector this size. Clean them, remove the tops with a can opener, and drill or punch a circular hole in the bottom of each one, about 1 inch in diameter, so air can flow through. Stack them end to end into columns using high-temperature silicone or simply friction fit them inside PVC guide channels. Paint every column matte black, flat black spray paint from any hardware store, 2 coats. Arrange the columns vertically inside your frame, shoulder to shoulder. Seal the sides so air cannot bypass the cans. Cut your 2 wall penetrations, a lower vent hole, roughly 6 inches by 10 inches, at the bottom of the collector where it meets the wall, and an upper vent hole of the same size at the top. These are your cold air inlet and your hot air outlet. Add simple backdraft dampers, flaps of thin plastic sheeting work fine, to prevent reverse flow at night when the collector cools. Glaze the front with twin-wall polycarbonate sheet. Seal the edges with weather stripping and aluminum tape. Mount the entire assembly on your south-facing wall, tilted at a compound angle that matches your latitude for winter sun. Roughly your latitude plus 10 to 15 degrees from vertical is the standard rule. The one critical rule you cannot skip: seal the glazing properly. If cold outside air infiltrates the collector box, you lose your temperature delta and the thermosiphon collapses. The box must be airtight, except for those 2 deliberate wall vents. Gary Race's Build It Solar project, available free online, has documented dozens of these builds with detailed plans, performance logs, and climate-specific modifications. For cold climates, consider adding a layer of bubble wrap between the glazing and the cans as a secondary thermal break for overnight hours. For humid climates, drill small weep holes at the bottom of the frame to prevent condensation buildup. This is not a complicated system. There is no controller, there is no battery, there is no inverter. The sun rises, the cans get hot, the air moves, every day, for decades. Now, let me be honest with you, because this channel has never been interested in selling you a fantasy. This system does not replace a full central heating system. On cloudy days, it produces nothing. At night, it produces nothing. If you live in a climate with fewer than 150 clear winter days per year, your results will be proportionally limited. It requires a south-facing wall with unobstructed sun exposure. If your house faces north or is shaded by trees, this particular solution is not for you. It is also not a weekend project in the sense of being trivial. Collecting 200+ cans takes time. The frame needs to be built squarely and sealed carefully. Wall penetrations need to be properly flashed and weatherproofed. Plan for 2 solid days of work, or 3 if you are new to basic carpentry. And it heats 1 room or 1 zone. It is a supplement, not a replacement. Think of it as permanently eliminating a portion of your heating bill rather than the whole thing. For a workshop, a garage, a sunroom, a single bedroom, the impact is immediate and real. For a whole house solution, you would need a much larger array or a different technology altogether, and we will get to those. These are not flaws. These are the honest terms of the trade. Permanent infrastructure for free energy in exchange for your labor and attention. That is a trade worth making. A lot of what this channel covers was nearly lost, not because it stopped working, but because the industry moved on to something more profitable to sell you. If rediscovering the lost art of high-performance, decentralized energy matters to you, subscribing and sharing is the simplest way to make sure this kind of knowledge keeps being found. And if you want to see how a simple earthen thermal mass wall, built from nothing but soil, straw, and time, can store the heat your pop can collector generates and release it slowly through the night, keeping your room warm long after the sun goes down, then you need to watch our video on Trom walls right here. The two systems were designed to work together, and together they are something the utility companies genuinely do not want you to understand.